In 1997, Stephen Hawking made a bet. He bet $100 and an encyclopedia that information falling into a black hole was lost forever. 27 years later, he conceded. He handed over the encyclopedia in front of a room full of physicists. He had been wrong about black holes, wrong in a way that took 30 years and the deepest tools in theoretical physics to fix. This is the story of that bet and the paradox at its heart that almost broke quantum mechanics. Quantum mechanics has a sacred rule: unitarity. The total information in a closed system never changes. It can be scrambled, hidden, encoded, but never destroyed. Now combine that rule with another fact, proven by Hawking himself in 1974. Black holes radiate. They slowly evaporate, glowing faintly with what we now call Hawking radiation, until eventually they disappear. So here is the paradox. You throw a book, packed with information, into a black hole. The black hole evaporates. What is left? According to Hawking's calculation, only featureless thermal radiation. The information of the book is gone, but unitarity says that is impossible. One of these two pillars of physics has to bend. Why does this matter? Because if Hawking was right, quantum mechanics is wrong. Every laboratory experiment that has ever confirmed quantum theory, every laser, every transistor, every MRI machine, would be operating on a foundation that fails inside a black hole. And if quantum mechanics is wrong, we cannot trust any of our predictions about the early universe, about subatomic particles, about anything. This is not academic. The information paradox forced physicists to choose. Either Einstein's general relativity is incomplete, or quantum mechanics is. For nearly 30 years, no one knew which. In 1976, 2 years after he discovered Hawking radiation, Stephen Hawking pushed the calculation further. The radiation he showed depends only on the black hole's mass, charge, and spin. 3 numbers. That is all. The textures of whatever fell in, the words on the pages of the book, the configurations of its atoms, are nowhere to be found in the outgoing radiation. Information, Hawking concluded, is irretrievably destroyed. In 1997, he was so confident in this conclusion that he and Kip Thorne formally wagered John Preskill, a Caltech theorist who insisted information must survive. The bet was $100 and an encyclopedia of the winner's choosing. Symbolically, an encyclopedia, a book full of information. Hawking's argument had a problem, and Leonard Susskind and Gerard 't Hooft, the same physicists who would later formulate the holographic principle, were the first to articulate it. Susskind proposed something he called black hole complementarity. From the perspective of an observer falling into the black hole, nothing strange happens at the event horizon. They sail through. But from the perspective of an observer outside, hovering safely far away, the infalling observer's information is smeared across the horizon, slowly leaking back out as Hawking radiation. Both observers are right, Susskind argued, because no single observer can ever compare their data. The inside and the outside are causally disconnected. This was the holographic principle in disguise. The information was on the boundary all along. Then, in 2012, 4 physicists, Almheiri, Marolf, Polchinski, and Sully, known as AMPS, discovered a fatal problem with Susskind's proposal. They proved that complementarity is mathematically inconsistent. To preserve information, the event horizon would have to be replaced by a wall of high-energy particles, a firewall. The infalling observer would burn instantly, contradicting general relativity's prediction of a smooth, gentle horizon. Either information is lost, or general relativity breaks at the horizon. The paradox sharpened. The resolution, when it finally came, was surgical. In 2019 and 2020, Jeffrey Penington and Ahmed Almheiri, working separately, used quantum extremal surfaces, a tool inherited directly from holography, to compute exactly how information leaks out of a black hole. They reproduced what is called the page curve, a precise mathematical signature of unitarity derived from the same ADS-CFT correspondence we explored in Episode 1. Information is preserved. The universe stays unitary. Hawking was wrong. 6 physicists, 43 years. One of the longest-running open questions in modern physics finally answered. Hawking gave us the radiation. Susskind and Hooft gave us complementarity. AMPS gave us the firewall. Penington and Almheiri gave us the page curve. And Hawking himself, in July of 2004, stood up at a conference in Dublin, conceded the bet, and handed John Preskill his encyclopedia. He had spent 30 years convinced of a calculation, and he changed his mind in front of his peers. That is what makes science different from belief. Stephen Hawking lost a $100 bet. The universe gained back its information. The paradox that almost broke quantum mechanics turned out to be the door to its deepest principle. That reality is more conservative than it looks, that nothing is ever truly lost, that even at the edge of a black hole, the bookkeeping of the cosmos remains intact. If you watched episode 1 on the holographic principle, you have already seen the tool that made this answer possible. Next, we trace one more idea backward, the strangest equation in physics, the one Einstein could not bring himself to accept. I will see you there.